So first, let's remember that a slope field is really showing you really important information or valuable information about the solutions of a differential equation without solving that equation. And oftentimes that's because you are unable to solve that equation. And really, when computer models solve these things, they're really just using a slope field in order to approximate the solution. And Euler's method is one of the easiest methods to wrap your head around. Now, more advanced methods are going to give you a more accurate approximation of the solution, but it's the one that we talk about. Euler is pretty big time in math, so we're going to look at his method, and that'll get you an idea. Remember that these are going to be approximations, not exact answers, but we're going to try to get really, really close. There are some things, some terminology and things that we want to get straight here first before we go on. The first thing is this f of ty here, and that is just your derivative written in a little bit different way. Okay, so if you're thinking of y prime, y prime would be the same as this f of ty, and t is the independent variable. Usually we're calling that x, but this is t for time here, and y is some unknown function. Okay, and so really, and hopefully you got this from the slope field stuff, videos from before. Really this is just slope. Okay, so f of t comma y right there, that is just slope at a specific point, t for time and y for an unknown function. And so that's what we're going to call that. Change in t is what they're calling a time step. Okay, so how far down the t-axis, right? Remember we're doing this. This is our t-axis and this is our y-axis. Again, t is time, y is unknown function. So the change in t is just going to be the time step. So how far down the t-axis are we moving before we do another approximation? And this u sub k is just going to be Euler's approximation for whatever step that you're on. So for step k here. Okay, so depending on how far down or how many steps we want to do, right, we would say, well, u sub 0 would be our initial value, and then we would have u sub 1, u sub 2, all the way until the end of our however far we're measuring out. Okay. And so to expand on that a little bit, we're going to say we're going to say u sub 0 is going to be equal to this y function evaluated at the time step sub 0, right? And that's going to be equivalent to whatever our initial value is. Then after that, these are all approximations. So this first step, u sub 0, is going to be given, and so that's going to be an exact step. And from that point on, we're going to use information to approximate each step from there. So it is important to understand that these are, of course, I just wrote equal sign, but these are approximations. Okay, so then we're going to evaluate y at the next time step, and so on. And so what we're going to end up doing is using the information from the previous step to approximate the next step, so to approximate future steps. So this is just a picture in the book, that I pulled off, and I'm going to kind of try to explain it the best I can here. Again, we're talking about slope fields, and at the very beginning of this, I mentioned how the f of t comma y was really equivalent to slope. Okay, so if you can picture yourself on this coordinate plane here, slope is just found the same way as it always was, right? We're talking about the change in y over the change in x. So, right, that's what we're doing here. U sub 1 minus u sub 0, right, divided by our time step. And so we're still finding slope the same way. And if you think about your slope field, right, there would be like a little diagonal thing here. And so then this would be pointing us up into this direction for our next step. And, so then this picture is just showing you in the opposite, in the negative direction. We'd have a little negative slope here pointing us in this direction, but it's really still just finding slope, right? The change in y divided by the change in t. And so that's kind of the relationship that I mentioned a second ago, that we're going to use this previous, in this case, u sub 0 is an exact answer, but these are going to keep changing as we move along our t-axis, whatever, right? But we're going to be using a previous piece of information to approximate our new piece of information. And so really what we want to do here is find u sub 1. That's what we're looking for. Remember, we're saying that u sub k is just the Euler's approximation. So we have this nice, neat formula here. Again, remembering this is slope. And we can actually solve this formula for u sub 1 or u sub k, depending on like what you want to do or like how you want to think about it. This, I'll just solve this one for the next step. Right, in our generic problem here. So what we have right now is this derivative. Remember, that's what it is. Remember, derivative is just a slope. And we already know, our initial value. These are initial value problems. So we already know this one, and now we want to know what this one is. So what we're going to do is solve. And so then we're going to multiply by the change in t, our time step. And then add u sub 1, add u sub 0. And so then our next step in this would be u sub 0 plus the slope, right? The slope of the original point. Again, this is our initial value. T is 0. When t is 0, we have this exact value for our y function, our unknown function here. Okay, and then let me, I really should make this, right? What's going on here? Really, what's going on here? Right, this is really an approximation at this point. Right, this is not equivalent necessarily, so it's an approximation there. Okay, and so now we can generalize this. So what we can say is that any future approximation that we want is going to be approximately equal to the previous approximation plus the slope I guess I should have used done this differently, but right, the slope of our previous point, I guess, times the change in t, our time step. And so now we can just use this approximation right here for any future approximations. And so now we're going to work through some problems. Okay, so then this is just what the book says is for our procedure of using Euler's method. And it's basically just what everything I just tried to say, right? So, right, we have this differential equation, okay, and we're going to say that, you know, this is what that is, remembering that a differential equation is just giving you the slope at a certain point. Our point now, a little bit different than what it was before. It's this value t, our independent value t, and with this unknown function y. Then we get this initial value, right? When t is 0, we have some initial value, they're going to call it a, on this certain time interval, right? 0 to however far out you want to go, okay? And now, you know, step 1 is saying we have to have a certain time step. And so you're either going to be given a time step or you're going to have to figure out your own time step depending on, you know, how small a step that you want. And all this is saying is if we did t minus 0, we'd have t, right, from the end of our time interval to the beginning, and we divided it by n, some number, okay, to break it into however many steps we're looking for. We have to have an initial value, right? It's going to be Euler's approximation. U sub 0 is equal to the initial value, right, when time is 0. And for each of these new k's, we're just going to inch down toward it. Okay, so you have to go through each step. You can't just jump down here because remember, right, it's saying each of these u sub k's is an approximation of the exact solution. So we won't have the exact solution other than when this very first step. So you can't just come down here and guess what it is. You would have to go through all these steps in order to get there. So here's an example for you. We're being asked to complete the given table with Euler's approximations for this initial value problem. Okay, and so, you know, all of these are really the approximations, okay, and then we're going to use the slope to find the next approximation. So I think the easiest thing is, you know, I'm going to fill out this chart, but I'm going to do my work down here below. So I'll have to scroll up and down to continue to fill in the chart, so I hope that's okay. So they've broken it down into this chart very specifically, but one of the things that we are missing is our time step. You know, they give it to us in a way, but I like to figure that out here first. So write each step is 0.25. Okay, so let's keep that in mind as we move on. And our first, you know, this is an initial value problem. And so then they give us this statement here. And so they started us at 1, like, you know, 1 time interval. You can think of it as seconds or minutes or whatever you want to think of it as. And then this is our initial step. So, you know, on a lot of the other problems, they're starting out at 0, 0, but it doesn't really matter when you start the clock, right? When you start paying attention. We still have an initial value of -1, so this first step is very straightforward, right? Our initial step is -1. And so now we want to use this information to find our first slope. So remember we have, you know, this is our differential equation and derivatives are just slopes. So actually this is going to be how we compute our first slope. Well, all of our slopes. But here's the notation for the first one. So our t is 1 here. and our y is going to be -1, right? And we're getting that from this step here, right? So we're on this first k step, and so we're just going to come up here and plug it in. So our y value is -1 minus our t value of 1. So then our first slope here is -2. So now we're moving on, and we want to find our next Euler's approximation. So that's going to be u sub 1. And so then I like writing it out like this because it helps me understand what I'm doing, you know. So what we're saying is okay, so this slope, oops, is also equivalent to right that. Okay, and you know what we want out of all of this is we want our u sub 1, our next approximation. Well, we already know the information here. We found that. We found the slope. And we now, sorry about that. We also know, my lightsaber pressed pause for me there. We also know the change in t. So I'm going to manipulate this formula just like I did before to get u sub 1 by itself. And when we're done with that, we would have this next Euler's approximation is the same as taking the first, in this case the exact solution there because it's an initial value, adding the slope times our time step. Okay, so then, right, let's go back up. Our first one was -1. And now we're going to add the slope, which was -2 times our time step. And so that's going to be -1 minus 0.5. And so then we're saying that is -1.5. Okay, so now we found the approximation here on the second step. And now we're going to have to use that information to find the new slope. So we're going to denote our slope this way, right? We move to the next step, so now we're finding the slope with these parts, right? And so remember, it's going to be y minus t. So that's -1.5 minus 1.25. So now our new slope is going to be -2.75. And now we're going to repeat the process. Okay, and to save some space, I'm not going to resolve the slope formula. You know, it's basically going to be this again, but just to save some space and time, you know, I'm just going to just solve it and just start down here. So our next step will be our next approximation is going to be using that previous approximation plus our new slope times our time step again. So I'm not going to keep solving that out, but I will say, like, I think it's helpful to keep solving this out so that you can kind of start remembering and understanding the relationship between all of this. But when I do these problems, that's what I do until I really have a good feeling about it. But I'm not going to do that just to save a little bit of writing and some time here for you. So then we're saying that this approximation is going to be equivalent to our, where'd it go, negative 1.5. That's what we just found as our u sub 1, right here. Plus our slope, which we have as negative 2.75. Times our time step, which again is 0.25. And when we simplify all that out, we get about a negative 2.188. And so I'm going to go add that to our chart. Okay, and now we repeat the process one more time. So again, we have to go down and find slope. And our new slope is oops, sorry. Our new slope is harder than it looks without being able to see the problem. This. Okay, and again it's y minus t. So then it's negative 2.188 minus 1.5. And so that's going to give us a negative 3.688. And now we can do the final approximation. Okay, so then again we're using the previous approximation and adding the slope. Hopefully this isn't too sloppy looking. And multiplying that by our time step. So again, our previous one was negative 2.188. Our slope, our new slope here is negative 3.688. Our time step is still 0.25. And so then our final approximation is going to be negative 3.188 1, 1. Okay, and so I'm going to come back up here. Okay, and so, we don't need this part of the chart anymore because we would only use the slope here if we wanted to find the fourth step, or when k is 4. So I guess that, I guess it depends on how you're looking at it. But we don't need this to compute the slope anymore. These are what you're really looking for. These are the approximate answers, the approximate y values for your function of the, where'd it go? There it is. Right? Whoa. Right? Of our differential equation. Right? We just use Euler's method to approximate this differential equation solution. It is important to remember that these are approximations, and you notice that we're just doing this cycle over and over and over and over again, and you're going to be given very simple problems to work with until you get to this section that says, use a computer program, and that's kind of an important point to understand. Doing these by hand is very tedious and can be very obnoxious and time consuming. And so there will be a problem that you get to that it's just several steps over and over and over again. But that kind of hopefully will drive home the point of what's going on and why a computer or a calculator program is very important and easy to use. And, again, this is pretty cool. This is really how calculators kind of solve any kind of differential equation, is they use slope fields and, not necessarily Euler's method, but a method that can get very, very close approximations. So I hope that was kind of gets you an idea. It's pretty cool stuff if you think about it. So please ask some questions if you got them.